Hello everyone and welcome to the Math Fun Room. We are going to begin chapter 11, and in this chapter we're going to ultimately be looking at what we call power series. One of the things we're going to do with power series is use them to estimate functions. Now, in this section in particular, 11.1, we're going to start to build the foundation for that conversation. We're going to look at sequences. But before we start that conversation, I just want to do a little bit of foreshadowing and show you one of the things we'll be doing with power series that will kind of allow us to have a little bit of a segue and lead into our conversation 11.1 on sequences. So a cool example I like to use is the power series for the function y equals sine x. So if we look at the polynomial y equals x estimates the sine function really well right around the origin. So in essence, y equals x is the tangent line to the graph of y equals sine x at the origin. So no surprise that it is a good estimator. So the graph of y equals x is our red graph here. And we can see, if we're about half of a radian above or below 0 radians, it's a really good estimate. Now, if we add the term negative 1 over 3 factorial x cubed to our line y equals x, notice that the estimation kind of spreads a little further from the origin. So now when we're about at negative 1.5 radian to positive 1.5 radian, this cubic polynomial does a really good job actually estimating the sine function. If I add another term, so here I have a 5th degree polynomial, we're going to notice this 5th degree polynomial is a really good estimator to the sine function, and it's even further out. So we can go a little beyond 2 radians, and the 5th degree polynomial is still estimating the sine function really, really well. And the more and more terms that I add onto this polynomial, right, the better the estimation is, further from the origin, if you will. So the idea here for power series is that the more and more terms we use in what we will ultimately call the Taylor polynomial, this polynomial function is a really good estimate to the sine function. And if we actually look at this idea of convergence, so we talked about convergence back in 7.8 when we looked at improper integrals. So on this page, we have the graph of y equals sine x, and we have the Taylor polynomial written in sigma notation. So again, this first example here is me graphing y equals x, and then here's the cubic polynomial x minus 1 over 3 factorial x cubed. And as I add more and more terms onto the polynomial, notice that this polynomial converges to the sine function. So this is just kind of a neat little thing to look at here initially is some foreshadowing. We're going to ultimately in the end of chapter 11 be looking at how can we estimate a function with a polynomial. And some of the reasons for that will be it's a lot easier to do calculus work with a polynomial than it is some of the other types of functions that we have. Really easy to differentiate a polynomial, to integrate a polynomial on its own. Okay, I could spend all day talking about power series, which I don't want to do here in this video. So let's go ahead and start the conversation on sequences. So in this first example, let's take a look at an application of a sequence. Now, again, remember what you learned in a pre-calculus course is a sequence is just a list of numbers. So in this case, we're going to consider the list of numbers that represents the number of fish in a lake in each month. So the problem says a lake initially contains 4,000 fish. It is known from breeding data that the fish population will increase by 7% each month. However, factoring in other causes, 25 fish are lost each month. The number of fish in the lake after n months can be described by the recursive formula a sub n equals 1.07 times a sub n minus 1 minus 25. And the question says how many fish will be in the pond after 5 months. Okay, the formula that we see being used here is what we would call a recursive formula. And the idea behind the recursive formula is that month N is defined in terms of the prior month. Now in this problem, they're telling us initially, so we could say month 0, right? But initially we have 4,000 fish in the lake. So to find the number of fish in the N equals 1 month, we're going to take 1.07. We're going to multiply it by the amount of fish initially and subtract 25. So we would end up needing a calculator here, obviously, to do that. So we'd have 1.07 times the 4,000 and then subtract 25. Whatever that number turns out to be would be how many fish are in the first month. Then to find the second month, I would take 1.07 and multiply it to the month prior, a sub n minus 1, and subtract 25. Again, whatever that number is that I got for month 1, plug it in there, take out a calculator, crunch that value. So let's do that. Let's lean on technology to calculate these values for us much quicker and more efficient. Now, if I'm using Desmos, the way that I'm going to do this is function notation, and I'm going to use the letter N. And using the letter N will have Desmos kind of identify I'm trying to do a sequence here. So I have my a sub n, or I'll write as f of n, being 1.07 times the a sub n minus 1. So I'll say f of n minus 1, and then subtract 25. And Desmos is going to prompt me for the base case. So obviously the base case being how many fish were in the lake at the end of the first month. So let's add that base case, and we're going to say the number of fish was 1.07 times the initial value of 4,000 minus 25. So that's how many fish we would have in the end of that first month. So when I add that base case, I'm going to come over here to the left and click to create a table, and it's going to create a table for me showing me how many fish are in the lake after month N. So to answer the question that we were being asked here, it was how many fish were in the pond after 5 months. So then we would look at n equals 5, and we would say 5,466 fish approximately in the lake at the end of 5 months. Now again, conceptually speaking, this illustrates the topic of this section, which is a sequence. We are writing out a list of numbers that identify, in this case, the number of fish in this pond after month N. Now what if I want to use a TI calculator to accomplish this task? So for a TI calculator, I'm going to need to start off by hitting the mode key, and I'm going to change the calculator to sequence mode. So we've been graphing in parametric and polar mode recently. Let's go ahead and change to sequence mode. And when I hit the Y equals screen, you're going to see we have sequences here. And there's a couple different options that the TI allows me to set. I'm going to hit my up arrow a couple times. I can have sequences as functions of n, or n plus 1, or n plus 2. Just depends on how the formula is written, on how I want to utilize that sequence formula. So for us, we had a sub n being 1.07 times the prior term. Now here in the calculator, it's using function notation of lowercase u. So if you look above, where is u at? Above number 5, I'm going to do alpha 5, and it's going to give me u. And then I'll put parentheses. I'll hit the variable button and say n minus 1. Close my parenthesis, and then subtract 25. Again, it's wanting to know what that case is for when n is equal to 1. So I'm going to go ahead and cheat, right? We had, 4255 is that value. So let's put 4255 there. I could also complete the value for when n is 2. I don't have to do that, but I could. So now when I go to the table, second graph, and go to the table, I'm noticing that I made a mistake in my formula. So let's go back and fix the mistake in my formula. Let me hit the Y equals. I used the wrong U. If you actually look above number 7 in blue is U. That's actually what I want to use here for my prior value. So instead of alpha number 5 that I used, I want to do actually second number 7, and it's going to use lowercase u, and that should define this properly. So now when I go to the table, second graph, and go to the table, we can see all of those values listed out for me in that sequence. Okay, so to just again come back and formally answer this question, how many fish will be in the pond after 5 months? We would say that there would be approximately 5466 fish in the lake after 5 months. Now this illustrates an example of a sequence where we're defining the sequence recursively. Let's take a look at a different example. Now this example says if you deposit $100 at the end of every month into an account that pays 3% interest per year compounded monthly, the amount of interest accumulated after n months is given by this sequence. I won't bother to read this formula here. And the question says find the first 6 terms of the sequence. Now you notice that this formula is not recursive, right? So this is just describing how much is the value, or what the value of the nth term is in terms of the variable n. So I don't have a sub n minus 1 or a sub n minus 2 here. I don't have prior values in my sequence defining the value of the nth term. We just have a function in essence. So when I utilize my calculator to do this, I'm going to use the TI again, and we'll use Desmos again. But this isn't recursive, so there isn't going to be any need to provide like a seed value or a starting value here. Now, actually, before I go to Desmos, let's just talk about how we would type this into Desmos. So because this isn't recursive, we can use a couple different varieties of ways to type this out. And what I really want is like a list. I want a table. So within Desmos, I'm going to actually add a table, and I'm going to type this formula into that table. So if I bring Desmos up here, I'm going to just go ahead and click to add a table. And then you can use the default letters that are provided here, or you can change to N if you want. But I'm going to go ahead then and type this formula in. All right, so I paused the video real quick so you didn't have to watch me type that out. But there's that formula. And again, I can really use any letters here that I want. So I chose to go ahead and just use letter N, and then here's the values for a sub n, and then I can type in n equals 1 and 2, 3, 4, 5, 6, 7, so on and so forth, and get the list of terms. Now just notice the way that this problem is worded is that this formula is giving us the amount of accumulated interest after n months. So if I come back to the list of terms, here's the first 7 months that we had out. At the end of month 1, we haven't accumulated any interest yet, because the way the problem is phrased is we placed $100 at the end of that month. So then in month 2, we're earning interest on that $100, and there's the amount of interest we have earned so far. And then at the end of the 3rd month, this is the accumulated amount of interest that we've earned. Right? So 75 cents of interest we've earned, and so on. Okay, so to use the TI here, so I'm going to type the formula in, as it is typed on there. Now, keep in mind that when I type this formula in, I'm going to have 1.0025 raised to the power of n. And again, I'm going to use the variable key because I'm in sequence mode, right? Minus 1. And then that was the numerator, dividing by 0.0025. And then we subtracted in. Okay. And then at the end of that first month, we had earned 0 interest. So I'll go ahead and put that value in. And then when we go to the table, we will see the list of values of the accumulated interest, just like we got out of Desmos. All right, so just pause the video real quick and took a screenshot, and there's the first 6 terms of that sequence. Now, in a more mathematical conversation, if we're looking at sequences, we want to know whether the sequences converge or diverge. Now, in the prior 2 examples, the amount of fish in the lake are growing and growing and growing, and over time, the number of fish in that lake or that pond go to infinity, if you will, right? At least based on that model. So that sequence is actually diverging. It's going off to infinity. Now, in reality, obviously, at some point, a pond isn't going to be able to sustain 100 million fish. But as far as the model that was there, those fish are growing and growing. And then same thing for that second example with the amount of interest that we're earning. Over the long term, our interest is going to grow and grow and grow and grow, at least based on the model presented. So the numbers in that sequence are getting larger and larger and larger, and they're going off to infinity in terms of a limit. We're going to say that that sequence is divergent. So the two terms, I won't bother to write them down here, but if you look in the textbook, the idea of a sequence converging is that the values of the sequence have a finite limit. So for the set of problems that we have here, the instructions say, let's first use technology to list the first 10 terms of each sequence. And does it appear whether the sequence converges? Right? And then second, let's use analytical techniques to determine whether the sequence converges or diverges. All right, so let's just focus on letter A for just a moment. So let's use technology to take a look at the first 10 terms of that sequence and see if we can observe whether those terms are approaching a finite value, if there's a limit, or whether they're growing without bound. Right, and I'm going to use Desmos for this first example. So let's add a table. I'm going to, just for fun, change the variable here to n. And then we had, what was our formula again? It was n divided by 3n plus 2. So let's do n divided by 3n plus 2. And then let's list the first 10 terms that was asked. So 1, 2, 3, 4, 4, 5, 6, 7, 8, 9, and 10. So looking at the list of numbers in this table, looks like the values are trying to approach a single number, quite possibly. I might need to go out a little bit further to observe that pattern. Looking at the graph, I kind of see the same thing. It looks like there's almost like a horizontal asymptote to these values, if you will. So if I wanted to, we could look at bigger and bigger n values. Right? So what's happening as n goes to infinity? What's happening as we look at infinitely many terms in this list? So if I look at the 20th term, look at all the way through to the 50th term, the 100th term, the 500th term, right? So we think of those ideas of a limit. What is happening to the terms as we look at the list of n going to infinity? And it looks like these terms are approaching 0.333, 1/3. So then analytically speaking, if we're looking at the limit of the sequence as n goes to infinity, a couple different ways we can analyze this limit. The numerator, n, is going to go to infinity. The denominator, 3n plus 2, that's like the line y equals 3x plus 2. Right? That's going to also go off to infinity. So the numerator on its own is growing without bound. The denominator on its own is growing without bound. And we could go back to the ideas in a Calc 1 class where we could use L'Hopital's rule. So since we have this indeterminate form of infinity over infinity, L'Hopital's rule says we can take the derivative of the numerator. So the derivative of x is 1. The derivative of n is 1. The derivative of 3n plus 2 would be just 3. So remember that L'Hopital's rule says that when we have this indeterminate form of infinity over infinity, we also had an indeterminate form of 0 over 0 back in Calc 1. Whenever we had a ratio that had one of those indeterminate forms, then we could take the derivative of the numerator all on its own, the derivative of the denominator all on its own, and then reevaluate the limit. In this particular example, when we use L'Hopital's rule, we end up just getting 1/3 as our limiting value, which is what we saw in the table. And so in this case, since this limit is a finite value, we're going to say that the sequence converges. And I'll just put over here, this is a finite value. Okay, so if this limit turned out to be infinite, we would say that the sequence is diverging. But in this case, the value is finite, and we will say the sequence converges. Okay, now for example B for this sequence, let's do this backwards since I'm here in the Word document. So let's take a look at the limit of that sequence Now, before we actually do the limit, let's just think kind of numerically, right? Let's analyze what's happening here. If we look at the numerator, the logarithm, right, the graph of a logarithm, come over here and sketch the graph of a logarithm. Graph of a logarithm grows pretty slow. The graph of n squared plus 1 is a parabola. That grows very fast in comparison. So for this fraction, the numerator's values are going to infinity, but they're going to infinity much slower than the values in the denominator. So even though the numerator on its own goes to infinity, the denominator on its own also goes to infinity, the denominator's values are going to get really, really, really large in comparison to the numerator and should drive these fraction values to 0. So since this fraction has this indeterminate form of infinity over infinity, we can do L'Hopital's rule. So if we take the derivative of the numerator, the derivative of the logarithm would be 1 over n. The derivative of n squared plus 1 would be 2n. So if I just flip and multiply this expression, I have 1 over n times 1 over 2n. And so what I really have here is 1 over 2n squared. So through L'Hopital's rule, we're now analyzing the expression 1 over 2n squared. The numerator is constant and stays constant all on its own. The denominator is quadratic, 2n squared. That is going to go off to infinity. And anytime we have something in the numerator staying constant, the denominator growing without bound, this limit is going to tend to 0. Now, since that is a finite value, we're going to say that the sequence converges. All right, let's go ahead then and do, again, this backwards. We did the limit analytically first. Let's take out technology and just check to see that this is a valid result for our limit. All right, and for the last one, we used Desmos. Let's go back to using the TI here. So the formula that we had was ln of n divided by n squared plus 1. I'm going to make sure I'm using parentheses here. Okay. Now, actually, I can leave this value blank and the TI will still handle it okay. I'm going to put it in anyway. When n is 1, I get ln of 1 in the numerator, and that's 0. So I get 0 divided by 2, which is 0. So that's my first term. The calculator will usually fill that out for me. So if I go to the table for a moment, and we take a look at the table, it looks like as we scroll down that as n goes to infinity, those values are getting smaller and smaller and smaller, assuming that that continues on to 0. Keep in mind in your TI, you can change the table format. So I can do second window and go to the table set, and I can start the table any place that I want. I can change the delta value in the table, or I can just go to the ask feature for the independent variable. Let's do that. And then now let's go to the table. Let's do second graph, go to the table, plug in n equals 10, plug in n equals 50, plug in n equals 100, and we're going to see what we already know from our analytical work. These values are getting smaller and smaller and smaller and going to 0. Now, obviously, the calculator is giving me scientific notation here, but I should be able to go up and move with my right and left arrows, and still keeping the value in scientific notation. Right? A lot of times, it'll show me a lot more decimal accuracy. Now, on a TI, we may have noticed from our prior example that the graph was appearing there as we filled that table out. And on a TI, we can also graph the sequence. So I should be able to just hit the graph key and see the sequence plotting. I'm in a weird window here. Let me go back to standard zoom and see what we get. So there's the sequence that it's trying to plot those points. Probably something to think about here is I can go to my window. Here's the values of n that's going to plug in. I don't need to see anything to the left of the origin. That was kind of useless there. So we could adjust our x-min, x-max, and then we already know that those y values were pretty small, so we could probably just look like between -1 to 1 in the y viewing window and then see the graph a little bit better. Now, something else to think about what the TI is trying to do here is like connect the dots, right? Remember that this is not a continuous function, that just like we saw in Desmos, what we're really doing is just plotting these values on an XY grid. So one drawback to the default of the TI is it wants to connect these dots. I should be able to change that by going back to my graphing screen and coming over here to the left. If I hit my left arrow a couple times, I should be able to hit enter and change this from a line. And I think if I go to the left a couple times, it'll show me just the dots. Now I click OK there. Now when I graph, it should just show me the dots that it's plotting, right, for each of those values. All right, now for both of these examples, the instructions said list out the first 10 terms in the sequence, and I haven't officially written those here on my Word document, all right? But obviously, I could go to my TI, and I could go to the table, and I could list those first 10 values if I want by looking at n equals 1 through n equals 10. You know, so I could go back to my table set. I could change this to auto. And then when I go back to the table, it'll fill those in for me, right? Or obviously, if I'm using Desmos, right, I'm pulling out those first 10 values that are there. Right? Now, if we go ahead then and take a look at the next one, letter C. So again, here we are looking at a sequence. The question really is, does the sequence converge or diverge? We're being told to, explore using technology, listing out the first 10 terms, and then we're being told to use analytical methods, which basically is, using a limit. So let's do this in the proper order this time. Let's look at 3 to the n divided by 2 to the n minus 3. So I'll come back to Desmos, and let's do 3 to the n divided by 2 to the n minus 3. One of the things I love about Desmos is it's easy to kind of zoom in and out of the window and see what's happening with the graph. And it's easy to adjust this table. But we can see pretty easily that, the first 10 terms are growing very quickly. We're getting up beyond 57, and it's going to get larger and larger and larger here. If I zoom out on my graph, notice that we're in essence getting something that's behaving like an exponential function, and those values are just getting larger and larger and larger. So if we think of the analytical work here, when we do the limit, we should be getting infinity out of the limit, and we're going to conclude the sequence diverges. Okay, so let's take a look then at the limit of 3 to the n over 2 to the n minus 3. Now, if we take the same kind of conceptual approach as we did in the prior two examples, we look at just the numerator, the graph of 3 to the x goes off to infinity, so the sequence 3 to the n also goes off to infinity. And then in the denominator, we have an exponential, similarly, 2 to the x, right? 2 to the n minus 3 is also going to go off to infinity. Now, using L'Hopital's rule here is going to be kind of a pain in the butt. Let's try to use it, and let's just talk about a way we could be a little bit more efficient first after that, right? So if we take the derivative of 2 to the x, the numerator is 3 to the x, 3 to the n. The derivative of 3 to the x is 3 to the x ln of 3. So the derivative of 3 to the n would be 3 to the n ln of 3. And then in the denominator, the derivative of 2 to the n would be 2 to the n ln of 2. And then the derivative of that minus 3 is 0. Right? So basically, in terms of a limit, the ln of 3 is a constant. The ln of 2 is a constant. So let's pull those out of the limit process. And we're looking at 3 to the n over 2 to the n. Now, if we're continuing to take this approach of L'Hopital's rule here, we're going to again get infinity in the numerator, infinity in the denominator. I'm going to do the derivative again. And again, I'm going to get 3 to the n ln of 3 in the numerator. I'm going to get 2 to the n ln of 2 in the denominator. And I'm just not going to go anywhere, right? Because the derivatives of exponentials are exponentials. So if we stop here at this moment, and let's think for a second algebraically, right? 3 to the n divided by 2 to the n is really 3 halves to the n. So what I'm really taking the limit of is an exponential, where the base is 3/2. So when we think about exponential functions, I'm going to come over here and sketch a graph, right? If we think about exponential functions like y equals a to the x, when the base is bigger than 1, that exponential function grows. So in this case, that's where we are. Our base of our exponential of 3/2 is bigger than 1. So we have a limit here that's going to go off to infinity because this is a growing exponential. Now, if the base is less than 1, the exponential decays. Right? So just kind of thinking back to our algebra days, right? If our base is less than 1, it's a decaying exponential. Okay? So I say all of that because I don't really want to have to use L'Hopital's rule from the beginning here. So doing L'Hopital's rule, we end up with a limit that's infinity, and we're going to say the sequence diverges. Okay, well, let's talk about a little bit more of an efficient way to handle this. So I would say in general, when we're dealing with sequences that have exponentials, instead of using L'Hopital's rule, let's use this idea graphically that we have, that we know about exponentials whose base is bigger than 1 grows, and exponentials whose base is less than 1 decays. So let's just re-look at 3 to the n over 2 to the n minus 3. And up front, we can just do a little bit of algebra to begin with. So what I'm going to do is divide everything by the fastest growing term in the denominator. So I'm going to take the numerator and divide it by 2 to the n, because 2 to the n is the fastest growing term in the denominator. And I'm going to divide every other term by that fastest growing term in the denominator. And technically, I still have my limit symbol here. So by doing this, here's what we in essence have algebraically. In the numerator, we have 3/2 to the n. In the denominator, 2 to the n over 2 to the n is 1. And then 3 over 2 to the n. Now, as n goes to infinity, we already talked about that term in the numerator, 3/2 to the n, that's going to infinity. And then in the denominator, the number 1 is constant, so it is 1. And then that last term there, the 3 divided by 2 to the n, that I just circled there. Right? So this is in the numerator something staying constant, and the denominator 2 to the n goes to infinity. So those values go to 0. So we in essence end up with, infinity over 1, and that is going to infinity. And again, that tells us that this sequence diverges. So my recommendation would be, if you have a limit you're trying to evaluate that involves exponentials like this one, you could definitely do L'Hopital's rule and get the results. Or you could just do a little bit of algebraic manipulation like we did here and take that original expression of 3 to the n divided by 2 to the n minus 3 and divide every term by the fastest growing term in the denominator. And that was a technique we actually learned about in Calc 1 back, I think, in Chapter 2 in this textbook, 2.4 or 2.5, I forget the section. I think it was actually 2.6. So we were evaluating limits at infinity, and one of the methods we learned about was taking the largest growing term in the denominator, divide everything by that term, and then evaluating the limit. The other process was to use L'Hopital's rule. Either one would work. Right? It really turns out to be personal preference at this point. But in summary, looking at this sequence of 3 to the n divided by 2 to the n minus 3, we're being asked to determine whether that sequence converges or diverges by exploring on technology, and then evaluating analytically, we can confer that this sequence is growing without bound, and therefore it is diverging. All right, in this example, let's take a look at 2 to the n times e to the negative n. And when I'm doing the limit here, I'm going to take that exponential of e to the negative n. I'm going to push it into the denominator using properties of exponents and make the exponent positive. So I really have 2 to the n divided by e to the positive n. And then let's just use that idea that we just talked about And let's write this as just one function, one exponential with the base of 2 over e. Now, when I look at the base of this exponential, the numerator obviously is 2, the denominator is e. Remember that e is approximately like 2.718 something, something, something. Right? That's an irrational number like pi. So I really have a base that's like 2 divided by something bigger than 2. So this base that we have here is less than 1. So just like we talked about on that prior, anytime I have an exponential whose base is less than 1, it's going to go to 0. It's going to decay. So from that knowledge, we know that these terms are going to go to 0. And since that is a finite value, we're going to say that this sequence converges. All right, now technically the instruction said we were supposed to write out the first 10 terms using technology, so let's do that. So bringing out the TI, I would have 2 raised to the power of n. And then we had, that was times e. So I'll do second ln. E to the, make sure I use the negative key here. E to the negative n. And then let's go to the table. Let's go second graph. We look at the table and we can see it appears those values are getting smaller and smaller and going to 0. Again, I could graph and see the graph on the TI. Looks like we definitely have a horizontal asymptote, if you will, right? And those values are going to 0. So this is a nice way to kind of visually check and explore to show that the analytical work we have is valid. All right, 2 more examples I want to look at here, and in these last 2 examples we're going to look at an alternating sequence. So we're going to notice a term, -1 to the n, that makes the values of the sequence change sign, alternate in sign. If you think about this, -1 to the power of 1 is -1, -1 to the power of 2, -1 squared is positive, right? So every time that exponent is even, that's going to be a positive value, and every time that exponent is an odd number, this is going to be a negative number. So we're going to have what we call an alternating sequence. So let's use technology to explore the sequence, and then we'll talk about the analytical work of doing the limit. All right, so I paused the video real quick just to list out the terms in the sequence here. So typing the formula into Desmos, here's the first 10 terms of the sequence. And again, notice that they're alternating in sign, right? First one is negative, second one's positive, third one's negative, fourth one's positive, fifth one's negative, so on and so forth. So every time that exponent has an even power, the term in the sequence is positive, and then a negative exponent, an odd exponent makes a negative term. And if we look at the graph, again, they're alternating between positive and negative. So we have negative, positive, negative, positive, negative, positive. And then, I jumped after sequence value of 10 to 20 to 50 from we had from a prior couple examples ago. But what looks like I have values approaching kind of a horizontal asymptote above and below. Now, even though these terms aren't going off to infinity, we're not going to say that they converge because they're not approaching one singular finite value. They're kind of approaching 2 separate values. So that behavior technically means the limit doesn't exist. So since the limit isn't finite or doesn't exist, we would conclude the sequence is diverging here. Okay. Now, let's take a look at the work analytically. Now, with that alternating term, actually what we're going to do is we're going to look at the absolute value of the terms as n goes to infinity. So taking the absolute value of the terms, I'm in essence getting rid of that alternating sign, and I'm just looking at the sequence and its positive values. Now, in evaluating this limit, technically the numerator 2n goes to infinity, the denominator n plus 1 goes to infinity. So if I'm using L'Hopital's rule, the derivative of 2n is 2, the derivative of n plus 1 is 1. And I can see that as n goes to infinity, in absolute value, the terms are going to 2. But because they alternate, what's really happening is the terms are going to plus 2, minus 2, plus 2, minus 2, plus 2, minus 2, so on and so forth. So what we're going to do in this case is we're going to say for an alternating sequence, we're going to look at the absolute value of terms. We're going to say something like this. If the limit of the absolute value of terms is non-zero, then the sequence diverges. Okay, so again, this kind of illustrates this example here. We're going plus 2, minus 2, plus 2, minus 2, plus 2, minus 2. So we want one singular limit. We need one finite value that we're going to approach. So divergence doesn't have to be going off to infinity. It also is the limit not existing, right? Not having one singular value in its limiting value. Now, we can also say the converse of this, right? That if the terms and absolute value go to 0, then the sequence converges. And I think the next example that we have is going to illustrate that idea. Okay. Now for the next example, we have another alternating sequence, -1 to the n times 1 over 3 to the n. All right, so using my TI calculator this time, I have typed in the sequence -1 to the n times 1 over 3 to the n. Again, making sure I use that negative key here when I'm putting in that alternating term, not the subtraction key. Let's see if I go to the graph. Kind of hard to see the dots. But here I'm getting terms that alternate, and they're going to 0 very, very fast. They're kind of getting buried under those tick marks. If I go to the table instead, I can see the values going to 0 very quickly. Right. Doing this also on Desmos, typing in the sequence, again listing the first 10 terms, we can see those terms going to 0 very quickly. And if I zoom in here, we can see the dots a little bit better, right? But the dots are definitely going to 0 very fast as they alternate. So we have negative, positive, negative, positive, negative, positive, and they get small very fast and go to 0. So when we do the limit here, because this is an alternating sequence, we're going to look at the absolute value of the terms, and we're going to be considering, do these numbers go to 0 or not. Now obviously from the graphical exploration, we know these terms are going to 0. But again, if we just think in terms behaviorally, in this case, in the numerator, the number 1 stays constant. The exponential 3 to the n goes off to infinity, and so that's going to go to 0. You could also think of that as 1/3 to the n if you wanted to. So we have the limit of 1 divided by 3 to the n, rewriting that as 1/3 to the n. That's an exponential. The base is less than 1, and therefore it is going to go to 0. So either way we want to think of that analytically, from the graph and that analytical work, we conclude that that sequence converges. Okay, so the last two examples we're going to look at here are kind of some fun challenge problems. What I always like about these is like you have to try to find the pattern. So like here's the sequence that we're being provided, and the challenge is how do we build the formula? You should have done something like this in a pre-calc class. Again, it's probably been a while and you forgot the approach. So let's take a little bit of time and just talk about really the two types of sequences we're going to generally encounter for now, earlier in chapter 11. So we usually encounter what we'd call a geometric sequence or an arithmetic sequence. A geometric sequence basically is a list of terms that behave in an exponential manner, and then an arithmetic sequence is a sequence that generally behaves in a linear pattern. So the formulas that we would get out of a geometric sequence will have a form that look like an exponential function, and out of an arithmetic sequence, they will look like a linear function. So when I look at this sequence here, it looks like the terms in the numerator are powers of 2. So, 4 is 2 squared, 8 is 2 cubed, 16 is 2 to the fourth. Looks like in the denominator I have the same thing. I have powers of 3. So, 3 to the 1, 3 squared is 9, 3 cubed is 27, so on and so forth. So it looks like I kind of like have powers of 2 in the numerator and powers of 3 in the denominator. And then I have, I have this alternating term that's happening there. So the formula that I just wrote is not correct. Let's adjust it, but I just wanted to kind of scribble down the idea that I have an alternating term, plus minus plus minus. I have powers of 2 in the numerator, powers of 3 in the denominator. So now let's just think about like where are we starting our n value? It's kind of a classic to start n at 1. So let's do that, but that's not a requirement. Just want you to keep that in mind. I mean, I could really start in at any value. I could start in at 0 and then count on, right? And in computer science, that's actually what you do. You start counting at the 0 index. Mathematically, you'll see both starting at n equals 0, n equals 1. If we start counting at n equals 1 here, and I think of the number 2 that I have, and then when n equals 2, I have the number -4/3. And when n equals 3, I have the number 8/9. And when n equals 4, I have the number -16/27. So if n equals 1, and I come back here and look at my incorrect formula, how am I going to get 2 out of that value? Well, the 2 in the numerator needs to stay 2. So it looks like I would have 2 to the 1. The 3 to the n in the denominator really needs to be 1. So what I really should have in the denominator is like 3 to the 0, so that I get 1 out of that. And then that's supposed to be a positive value. And if I plug 1 into that alternating term, -1 to the power of 1 is negative. So I think I really want like -1 squared to start. So that would give me a positive 2 out of that first term. And let's think of the relationship here. So when n was 1, the power of the 2 was the n. The power of the 3 was 1 less than the n. And the power on the alternating term was 1 bigger than the n. So maybe what I have is a 2 to the n in the numerator. I have a 3 to the n minus 1 in the denominator, and a -1 to the n plus 1 in the numerator. So let's see if that works for the next term. So when n is 2, I would have 2 squared in the numerator. I would have 3 to the 2 minus 1 in the denominator, and I would have -1 to the 2 plus 1. So that would give me -1 cubed. That would give me 2 squared and 3 to the first. And that would give me that term. That would give me -4/3 for that second term. So that looks like that will work in this case. So it appears that for n starting at 1 as my counter, if I write this as -1 to the n plus 1, 2 to the n in the numerator, and 3 to the n minus 1 in the denominator, that formula, that is my a sub n, that is the general term of that sequence, and that will produce all of the terms. Now, the first part of this problem was find a formula. We have accomplished that. Then it says determine if the sequence converges or diverges. So since this is an alternating sequence, we're going to technically want to consider the limit of the absolute value of the terms. So for determining convergence, let's ignore that alternating term. And let's just look at 2 to the n over 3 to the n minus 1. Okay, a couple different ways to think about this. I think the easiest way is going to be to look at that denominator as 3 to the n times 3 to the -1. So in other words, in the denominator, if I multiply 3 to the n and 3 to the -1, there's like bases of 3. I add the exponents and get 3 to the n minus 1. So I'm kind of like going backwards. Okay. And the reason that I did that is technically 3 to the -1 is a constant value. So I'm going to take out the 1 over 3 to the -1, and that's going to multiply the limit of 2 to the n over 3 to the n. And then just like we did earlier with those exponentials, this is an exponential here. of 2/3 to the n. And that exponential is a base that's less than 1, and so that's going to go to 0. So since the absolute value of the terms are going to 0, then this sequence is converging. Okay. So let's just write that out in summary. Isn't it fun? I love so those are challenging to try to look at those list of terms and come up with that pattern. So again, the two types of patterns we're going to typically see in this course are geometric, which means it's exponential in behavior, or arithmetic, which means it's linear in behavior. So this very last example is something that is arithmetic, and we can identify the arithmetic behavior here by kind of the idea that there's a common slope, or really a common difference between the two terms. So in other words, like when n is 1, we have the number -4. If I add 3 to that, I get to the next term. So when n is 2, I've added 3 to the prior number. So this was like -4 plus 3. That's where that number came from. And then if I start with this term of -1, if I add 3 to that, that gets me to the number 2. So I'm getting like -1 plus 3. And then the next term, when n is 4, I'm starting at 2. If I add 3 to that, I get 5. Okay. So in other words, like I could say the next term in the sequence is the term prior, where I add 3 to it. So I'm adding 3 to every number to get to the next number. Now, this is a recursive formula. And the only, I didn't spell formula right. This is a recursive formula. And the only problem with the recursive formula is when I'm trying to do analytic work. So like if I'm taking a limit as n goes to infinity, it's difficult to use like our prior limit techniques to evaluate this limit here. Okay, so we can't like do L'Hopital's rule, if you will. However, if we just look at the pattern of the numbers here, if we're adding 3 every time, those numbers are just going to get bigger and bigger and bigger and bigger forever and ever, right? I mean, that's going to go to infinity like a linear function. This is kind of like y equals x plus 3 in a way. It's not really its official equation, right? But these terms are getting bigger and bigger over time. So the limit of a sub n plus 1 as n goes to infinity being a sub n plus 3 tells me that that's just going to go off to infinity forever, and this is a sequence that diverges. Now, let's say that the instruction stated we need to find the nth general formula that's not a recursive version. So, not a difficult thing. This is a line. These points in the sequence are behaving linearly. So basically, I'm going to think of this as having 2 points on a graph. So in other words, like when x is 1, y is -4 is a point, and when x is 2, y is -1, and I can just find the slope of this graph and find its equation. So the slope between these 2 points is 3. We already know that. 3 is what is being added to get to the next point. Okay, that is our slope. And then let's just take that first ordered pair where x is 1 and y is 4. Okay. So if we solve for y here, what are we going to get? 3x minus 3. This is plus 4 on the left-hand side, so I subtract 4 to get it to the other side. So I get y equals 3x minus 7. So in other words, I can write this formula as a sub n equals 3n minus 7. So if I plug in n equals 1 into this formula, I'm going to get 3 times 1 minus 7, which is negative 4, and that is the first term in our sequence. If I plug 2 into this formula, 3 times 2 is 6, minus 7 is negative 1. That's the next term in my sequence. If I plug n equals 3 into that formula, 3 times 3 is 9, minus 7 is 2. That's the third term in my sequence, so on and so forth. So if the instruction said give a recursive formula, we provided that. If the instructions say find the nth general term, which is actually what the instruction in this problem asked for, then this would be the nth general term for all of the numbers in this sequence. A sub n equals 3n minus 7. And then the advantage to that nth general form is now when I do the limit as a sub n, do the limit of a sub n as n goes to infinity, I'm looking at the limit of an algebraic equation, which of course we know that line goes off to infinity and that sequence diverges. Okay, so that wraps up everything we would really want to talk about in this section, right? Real quick in summary, we started off with a little bit of foreshadowing. We were talking about a power series and having a terms added together, converging to the sine function. That was the example that I like to use to illustrate that idea of convergence. Also, what I like about that idea is it talks about taking a list of numbers and adding them together. That addition of the terms is what we call a series, which we technically don't do in this video in 11.1. But what we do look at is a list of numbers that we call a sequence. So based on having a list of numbers, the concept in this section is given a sequence, how can we determine whether that sequence is converging or diverging? We can explore graphically and numerically, and then we can justify our observation using analytical methods of evaluating a limit as n goes to infinity. So to see the behavior of the terms in the sequence and what they are doing, what they look like. So if you have any questions, please let me know, and I will see you in the next video.